We now turn to the main part of the course, which is the study of the three sections of a cone, or conic sections, called the parabola, the ellipse and the hyperbola. We'll begin with the parabola, but we will define all three conic sections using the same definition. So let us first of all consider the idea of a conic section being the locus of a point which moves so that its distance from a fixed point to the distance from a fixed line stays in the same constant ratio as the point moves. So we have a point which is fixed, called the focus, S. We have a fixed line which is called the directrix, and each of these three conic sections have the property that for any one of them the ratio of the distance of any point on each from the focus to the directrix stays the same, and that constant ratio is called the eccentricity, and it's denoted by the letter E. So on this diagram here we see a fixed point S, the focus, a fixed line called the directrix, and we take a typical point P, which is going to be on the conic section, be it a parabola, an ellipse or a hyperbola. Now when we talk about the distance from a point on the locus to the fixed point S, the focus, that's easy, that's clearly this length. But when we're talking about the distance from a point P on the locus to the directrix, we mean the shortest distance, or the perpendicular distance. In other words, the distance from the point P to the line, the directrix, which meets it at M, where PM makes a right angle with the directrix. And so for any of the parabola, ellipse or hyperbole, then the ratio of SP to PM, so this ratio is the number E, the eccentricity, and that stays the same for all points on the locus. Now the three cases that we're going to look at is first of all where that ratio is 1, so the eccentricity is 1, and that's called a parabola. So that will be all points for which P is the same distance from the focus as from the directrix. When E is positive but less than 1, we get an ellipse, and when E is bigger than 1, we get a hyperbola. And we'll study those two later on. For example, for the ellipse, it means the ratio of S to P to M, which is the distance from P to the focus and P to the directrix. That ratio is a number less than 1, say a half. Now for the parabola, two obvious examples that one can see in real life will be the path of a ball as it travels through the air. For example, a cricket ball, that will follow the shape of a parabola. Or if you look at the cross section of a satellite dish or a headlamp, that for very good reason is in the shape of a parabola. So taking that definition for the parabola, in this diagram here we take the fixed point S as shown, the focus, and the fixed line which is the directrix as shown, and we locate the x-axis to pass through the focus and perpendicular to the directrix. We also take the y-axis, which is perpendicular to that, to be midway through the focus and the directrix, just to make the determination of the locus easier. Now clearly the point O, which is the origin, is the same distance from the focus as it is the directrix, and because the ratio of the distances from S to a point on the locus to the point on the locus to the directrix has to remain as 1, then clearly the vertex, the origin here as it's called, is a point on the parabola. Now we've also shown a few other points, and say for example this point P here, that distance PS is the same as PM. So our task is to determine for any point on this locus, in terms of its coordinates x and y, a relationship between those two. If we join up all those points, you'll see by considering a number of different cases we get a smooth curve, and that's going to be the shape of the parabola. Very familiar to you, except you normally draw your parabolas as a U shape like this, and this is exactly the same shape but just turned on its side. So as I said before, this lowest point, the point if you like to the left on this diagram, is called the vertex. It's at the origin. So determine the Cartesian equation for a parabola. It's very straightforward, because first of all, if we assume that the focus is at the point a, 0 for some positive value a given, and the directrix, which is meant to be equally placed away from the origin, is at x equal minus a, and if we label the point P on the parabola with the coordinates x, y, then from Pythagoras' theorem we can work out SP squared, as shown here. Equally, we have that the distance from P to M is the distance x plus this length here, which is of course a, where a is positive. And so with these two distances, we can interpret the definition that SP divided by PM being equal to 1. In other words, SP squared is PM squared, by substituting in these two expressions. So if we do that, as shown at the top here, multiply out, cancel and rearrange, we get the standard form for the Cartesian equation of a parabola, where A represents a parameter which is fixed, and it denotes the x coordinate of the focus on the x-axis, and the directrix x equal minus a. So y squared equal 4ax represents all points P that are the same distance from S as they are from M. Clearly, if you were to interchange x and y here, you would get a relationship of the form y is proportional to x squared. A very familiar parabola, but again shaped upwards here. If you interchange x and y, then that's just reflected so that it becomes a parabola as shown here.